Hi all. I'm not going to make as formal a set of videos as I put out there for the first set of videos. What I'm going to try to do moving forward is to make these type of example problems and semi-lecture notes, and I'll just quickly go through them. So I'm not going to worry about them being as polished as I can make them just to get them out there. So what I'm doing here is an example problem of flow over a flat plate. So what we have over here are a number of plates that are coming out of a heat treating furnace, and they're moving from left to right at a relatively slow rate, and there's subject to a cross flow of air at a velocity of 10 meters per second and at a free stream temperature of 20 degrees C. So while the states here that the velocity of air is much larger than that of the plate. The reason why this is that if the plates were moving fast, then we would be in a situation where it wasn't exactly flow over a flat plate, because there'd be an impinging jet where you'd be coming in at the plate at an angle, and our correlations don't are not appropriate for that type of situation. The other thing to point out is that this diagram is not to scale, because the plates are square 1 meter by 1 meter, but they're only 6 millimeters wide. So this is essentially very thin sheets of sheet metal. Okay, so the plates have an initial temperature of 300 degrees Celsius, and they want to know what is the rate of heat transfer from the plate, and also what is the corresponding dT, the time rate of change of the temperature. So let's go through this. The geometry and temperature of the plates. So length and width are a meter. The thickness is 6 millimeters, and the initial surface temperature is 300 degrees, all given in Celsius. The infinity temperature is 20 degrees, and U infinity is 10 meters per second. So if I utilize those two temperatures, I'll get the film temperature to be 433 degrees. So if I go over here to my properties of gases, in this case of air, I have columns, or rows rather, for both 400 and 450. So as before, I'm just going to go ahead and interpolate, and for most of these problems we only really need the kinematic viscosity, the thermal conductivity, and the Prandtl number. So those are the three that I'm doing in regards to determining what these values are. Once more, I want to point out that these exponents here, what this is basically saying is that this table is giving the kinematic viscosity as being 26.41. And what they're saying is that's 26.41 after it has been multiplied by a factor of 10 to the 6. So the real value of this is 26.41 times 10 to the minus 6, because if you have 26.41 times 10 to the minus 6 and then multiply that by 10 to the 6th, you come out to 26.41. So all of these, so the viscosity is 10 to the minus 6, the thermal conductivity is 10 to the minus 3, and the Prandtl number is just a value between 0 and 1, so it really does not have, well, it can be greater than 1, but it doesn't have any exponent associated with it. All right, so for this problem, we'll again assume, we're not told otherwise, so we'll assume the critical Reynolds number is 5 times 10 to the 5th, and if we look for where the transition point is, we find that it's at 1.56 meters. So that's a length that is longer than the plate itself, so that means that we'll have laminar flow over the entire plate. With that being said, I can then now utilize the laminar average correlation to get the Nusselt number. And before I do that, I need to calculate what the total Reynolds number is, or the Reynolds number at the trailing edge of the plate. And to do that, we have U infinity times the length of the plate divided by the viscosity. So we have, so this would be read it as 3.1 times 10 to the 5th, which is obviously less than 5 times 10 to the 5th. So we're laminar. We determine the average Nusselt number as 331. From the average Nusselt number, We can then get the average heat transfer coefficient as being 12.1. Again, I'm not putting units in here, but again, remember this is watts per meter squared per Kelvin. And then the total heat rate, the total rate of heat transfer from each side of the plate, right? This plate has two sides, but where this Nusselt number correlation is only for a boundary layer on one side of the plate. So from one side of the plate, h bar times the width of the plate times the length of the plate times the temperature differential is 3,399 watts. To get the total heat transfer from the plate, we have to multiply that by 2 to account for both sides of the plate. So I state here in the yellow, the total heat rate from the plate with both sides, and of course we're neglecting that small area of the perimeter, but it is very, very small with respect to the area of the two sides, is 6,798 watts. If I was reporting this as a final answer, I would only use 3 significant figures, so this would end up being 6,800 watts. However, I'm going to utilize this in the next computation, so I keep at least 4 significant figures. So the rate of change of the temperature of the plate, we just apply the first law. So we have E dot in minus E dot out equals the rate of change of the energy stored within the solid itself. So we're told that the material is AISI 1010 steel, so we get the properties of its density, its specific heat, and the volume, right? This capital V here is the volume. So it's the length of the plate times the width of the plate times its thickness. And with those calculated, we note that E dot in is 0, right? There's no source of heat coming into the plate. There's only a source term going out, and that's going to be equal to the time rate of change of energy within the plate. So once we do that, we get that the time rate of change of the temperature is negative 0.333341. So again, stating this in 3 significant figures, we get that the initial, and this is the initial rate of change, because as soon as this starts happening, the surface temperature of the plate starts decreasing, so we would have to cycle back again to determine a new Nusselt number. So this would be an iterative process that we could take a look at, which we're not going to right now. So the rate of change of temperature of the plate is about 1/3 of a degree per second, and it's decreasing. That's what's being stated by the negative sign.